Okay. Welcome to the ninth presentation in the third webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to the advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of the adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been a immense success, and the recordings of the previous webinar continue to be viewed on YouTube and Webley. This is the ninth webinar of our third series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the third series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Professor Paul Webley of Monash University in Australia. I'm Junpei Fujiki of Nagoya University. Today's webinar will be moderated by Gonkei Xiao at the University of Western Australia. We are required to remind attendees and future viewers that views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institution associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. You are minimum only $20 per year, but support the publication of our flagship journal, Adsorption, contributed to travel grant workshops funding for IAS members and affiliated groups, as well as the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter for future updates regarding the IAS events, webinars, and information about scientific meetings. Please help us expanding our YouTube channel and Webley by liking this video and subscribing. The IAS Education Committee is happy to announce the third IAS Twitter Poster Conference that will be held between December 5th and 9th, 2022. This is a no-cost event to promote the research of graduate students and early career researchers. Registration is required to be considered for one of 6 monetary best poster prizes. Register and post your poster before the 5th with hashtag IAS Twitter Poster 3. More detail and the registration link are available on our website. Now, I hand over to Gonkei Xiao, who will moderate this webinar. James, please.
Hi, everyone. I'm Gonkei Xiao. So now I'm going to introduce the speaker. So Professor Paul Webley studied chemical engineering at the MIT, where he received his Master's of Engineering and PhD degrees in chemical engineering in 1986 and 1990. From 1990 to 1992, he was an assistant professor and a director at the School of Chemical Engineering Practice at MIT. In 1992, he moved to Air Products and Chemicals as a senior process research and development engineer. And then in 1996, he was appointed as a senior lecturer at the Department of Chemical Engineering at Monash University and was promoted to reader in 2003 and then professor in 2008. In 2012, he moved to the University of Melbourne as a professor in the Department of Chemical and Biomolecular Engineering. And since 2020, he has been a professor of chemical engineering at Monash University and the director of the Woodside-Monash Energy Partnership. Professor Webley has authored more than 300 papers in scientific journals and books, and his work has attracted more than 18,000 citations. Also, he has held many important posts related to environmental technologies, especially related to CCUS. And more importantly, he is currently the president of the International Adsorption Society. His principal research interest is in technologies for environmental and energy applications, including CO2 capture and utilization systems for the industrial and energy sectors, hydrogen generation, storage and utilization technologies, design of energy efficient thermodynamic systems, and negative emissions technologies. Over the past 25 years, he has significantly impacted the design and implementation of adsorption-based carbon capture technologies. And now he's taking the enormous challenge of CO2 conversion for a cleaner future. So now I'm going to hand over to Paul. So while we are setting up, I remind the audience that during the webinar, questions can be submitted to the speaker either via the Q&A tab of the Zoom meeting or as the comments on the YouTube live stream. Paul, now the stage is yours.
Thank you very much, James. And just checking that you can hear me and see my full screen, full slideshow. I'm assuming that's all, all good to go. Thank you very much for that very kind introduction. And I'm very privileged and very happy to give this seminar today. And very pleased to be able to welcome everyone who is attending today, and as both as president of the International Adsorption Society and also as an individual who's worked in adsorption systems for many, many years, going on, I was checking today, maybe 30 years now. And so I'm very, very happy to be able to give this presentation. And the title is Design, Operation and Analysis of Pressure Swing Adsorption Processes. I include in that title vacuum swing adsorption processes, so anything where we're relying on pressure to cause the separation. So with that introduction and with James's very kind introduction, I'd like to get started. And today I'm going to work through in this tutorial something that's a little bit different that you won't find in textbooks and you won't find in papers. They are a brain dump of my experience of 30 years in working at the interface between universities and industry in this very fascinating field of pressure swing adsorption. So my happy space to do my work is between universities, learning about materials and how to operate them, and then applying them in industry. And I'm happiest when I can see the fruits of my labor from the universities and from the research lab applied in industry and actually working and benefiting humanity. So what I'd like to do today in my presentation is work through these various topics. I think it'll be about an hour. And I'm going to start in an unusual way. I'm going to start with what I call PSA workflow. And the reason for starting like that is to answer the very important question, before we even start as both academics or as engineers, if you're working in a company, why are we doing what we're doing? It's easy to answer what we're doing. It's not always obvious why we're doing what we're doing. And the PSA workflow, in my mind, is the framework to answer why we're doing what we're doing. So I'd like to structure my entire tutorial around the PSA workflow. So within that workflow, I'm going to identify some key areas that I think are really important. One of them is modeling and design. One is lab and pilot work, some scale up, and then I'll conclude with a little bit of operation control and troubleshooting. So today you're going to see very little mathematics, very little chemistry, very little materials characterization. You're going to see a lot of experience of 20 years of going from very fundamental all the way through to building and running a plant. So hopefully you will be able to learn something today and get something that could help you in your own work. So what do I mean by PSA workflow? What I mean is pressure swing adsorption, PSA. What are the steps that I go through in order to go all the way from step one all the way through to the end of the process, which is building a pressure swing adsorption plant and operating it. So step one is if you're an engineer working in a company, perhaps an industrial gas company, or if you're an academic working at a university or you're a PhD student and you've thought of an idea, everything always starts with an idea. Someone has an idea for a separation. They look at a separation that's currently done, perhaps by distillation, and they wonder, can we do that separation by adsorption? Or they read a paper and they find a really interesting adsorbent material which can separate two molecules based on the adsorption isotherms, and they ask, that's interesting. Can I take this and actually create a process, build a process and actually use that material? How would that material perform? So usually I know before I start from the application, I know what temperatures and pressures and concentrations that I need to be concerned about in my application. For example, if someone says to me, have you got an interesting process that can separate ortho and paraxylene in the hydrocarbon industry? Well, I know if I go and look in the hydrocarbon industry, I know what concentrations those two molecules are at and what temperatures and pressures. So that bounds my problem a little bit. Or if someone says to me, I've got two isotopes of hydrogen I want to separate, and I've found an interesting adsorbent, I kind of know what concentrations and temperatures and pressures I have to be dealing with. So everything starts with an idea, but that's of course not good enough. So if I went to my boss in the company and I said, I've seen this really interesting adsorbent, or I've got this interesting request from a customer who wants to look at this separation, and I found this adsorbent, what do you think? Your boss may turn around and say to you, well, go away and spend a week looking to see if you can find some isotherms, some idea of the material. Is it a very exotic material? Is it possible to manufacture it? Is it a irreversible chemical reaction on the surface, or is there something where you can adsorb and desorb? And you might decide that between your day job, you're going to spend a week or so just exploring what that material looks like. There's no cost to that, and it's something that you may find something that's really interesting. So that's the first part of the workflow, and that's really just based on looking at isotherms, perhaps looking at kinetics, maybe not even at that point. Also looking really importantly at this stage, I'm thinking about the adsorbent that's reported. Perhaps it's a very exotic metal organic framework, and asking, am I ever going to be able to get this at hundreds of kilograms scale in the next 5 years? Is that possible? So those are the sort of constraints that might inform you at that point. And so I like to think of all technology development from universities and from labs into industry. I like to think of them in terms of stage gates, and there's various gates that we place in the process as we progress, and they provide us decision points where we decide to progress or not progress. So if after a week I've looked at this and I've found some really interesting materials that look like they absorb well, they look like they have a good separation between the molecules, they look like they're physisorbed, relatively easy to adsorb and desorb, the material looks like could be something I could make reasonably easily. So maybe there is a prospect. And I go to my boss and I say, or go to my academic supervisor and I say, I think it's possible that we could use this material. Let's have a little bit more serious look at it. And your boss may say, okay, why don't you go away? I'll take you off your current day job for 3 weeks. It'll cost me a little bit of money, but not too much, maybe only, depending on your salary, maybe only a few $1,000s. And go away and do some very early stage process calculations, not detailed PSA simulations, just very early stage calculations using some simple models. Tell me roughly what I'm looking at. What's the temperatures and pressures? What roughly is the size of the plant? Can I get this adsorbent material in scale? Give me a plus or minus 50% business case for why I should continue with this analysis. If you find that after your initial considerations, no, I can't really see an easy adsorbent, then at that stage gate, you stop the process. If the business folks say, I think you should go back because this is such an important separation that the client wants, maybe we should go and develop adsorbents, then maybe you go back and you think about that. So once you've decided that you're going to go and your boss has given you approval to go away and do some early stage calculations, and I'm going to talk through some of these a little bit later in the tutorial, how we do these. Things to think about at the early stages are, what sort of cycle should I be using? Is it pressure swing cycles? Is it temperature swing? The streams that the customer wants me to look at to separate these molecules, maybe it's hydrogen from ethylene. What are the impurities are in that stream? Impurities are very important in PSA. They make or break the operation and success of a PSA system. So impurities are very, very important to consider very early in the design piece. It might be that the engineering cost of handling the impurities is so severe that it completely discounts using PSA altogether. So it's important at an early stage to consider impurities. And you want to get some idea of the approximate pressures and temperatures, roughly what sort of size vessels, roughly what sort of capital costs. And these are numbers, rough numbers you can put together. So you go back to your boss after 3 weeks. He's spent a bit of money for you to do this. You don't have to involve a lot of other people. And you look at this and you go, well, this is really interesting. Is there a business case that we can actually deal with this? And your boss may look at this and say, from a business case, yes, that's very prospective. I think it's worthwhile for you to go on secondment for 3 months. And that's going to cost me a bit of money, but I've got it in my budget. So go away and do some more detailed work. So now I want you to go and do some PSA simulations. You may have to ask our R&D department to do some isotherms. If you're in university, you may have to go and measure some isotherms, get some more data, different temperatures, pressures, draw up some sketches of what the PSA would look like. What does the balance of plant look like? What does the interface to the customer look like? Refine some of those economic calculations, get some more engineering work around this. It won't cost me too much, maybe only $20,000, $30,000. I could probably afford that. But this would really give me a little more confidence that there is merit in this case. And for those of you working in academia, this might be something where you've developed a new metal organic framework, but you want to take it a little bit further. You want to actually take that metal organic framework and assess how it would behave in a process, and to get some more isotherms, do some detailed PSA simulation, and provide this very pre-feasibility kind of analysis of the prospect for this new material. If after that early stage 3, the business case is no, it's very marginal, even in plus or minus 50%, it still doesn't make sense. Well, it's important at that stage that we identify what we've done. We document what the issues were. Why wasn't it successful? Was the CapEx too high? Was the OpEx too high? What were the issues? Because those issues may go away in the future, or the product that you're trying to separate might become much more valuable in the future. And as a result of that, it might make more business sense in 10 years' time. So let's not throw away the idea. Let's just document, put a pin in it, and see and come back to it later. So after your, let's supposing you've gone through to stage 4, you've done the detailed simulation work, you've done some much more refined calculations, and you go back to your boss, or you look at the business case and you say, this really does look very good. Even in the time frame with the development budget included, this still is looking very prospective. Then your boss basically has to take a decision, or you have to take the decision if you're the boss, that yes, we're going to start this project. This is now a serious project. It didn't just cost $10,000 or $20,000. I'm now actually going to launch into a much larger scale study. And from my experience, where we're at in the world at the moment in PSAs, we still are not comfortable enough to go from isotherms to PSA simulations to building a $20 million or $50 million plant. We still have to build an experimental version of that plant before we build the big one. And so you're going to have to go through this process of experimental work. And that experimental work is costly. It's costly both in terms of equipment, and it's also costly in terms of people. And so I've said there 9 to 12 months, but it could be much more if it's a complicated separation. If you're looking at a hydrocarbon separation or a hydrogen methane separation or anything involving combustible dangerous gases, There's another layer of safety and protocol that costs a lot of money. But there is nonetheless a requirement in PSA development to do a large experimental work component in which you actually run experimentally the PSA. You understand the isotherms, you understand the material sensitivity and stability, how long does it last, is it sensitive to temperatures? You understand the PSA cycles that you have to operate, you get data on the cycles, the step times, the scheduling, the control strategy. You've also then go back to your simulation models and make sure that they're matching your experimental data. That gives you more confidence. You identify engineering issues. It's also a really good time, if you haven't done so already, to contact the adsorbent manufacturer and have a discussion with them about the adsorbent that you plan to be using in your system. Is it just a commercial adsorbent which needs perhaps ion exchange? Is it a brand new adsorbent? Is it a metal organic framework that has a very exotic synthesis? If so, understanding those timelines is really important, because for a adsorbent manufacturer to establish a new production line for a new adsorbent material will take many years and cost a lot of money. And there has to be, for them, a good business case to do that. And so this definitely is something that you need to engage in before you yourself spend a lot of money only to find out that you can't procure the material that you want to procure. So this is a serious investment of a company or of a university. Many universities don't do this stage because it's an expensive stage to do, but some universities increasingly do the stage of experimental PSA testing. And I'll talk a little bit later a lot more about the experimental PSA testing. And once that work has been done, and assuming that it still is confirming the simulations and it's really just providing more security, we then go to the full feed, front-end engineering design, where the PSA is then designed and scaled up from the lab data. We do the balance of plant, the additional equipment needed, detailed economics, quotes from vendors for equipment, timelines from the adsorbent supplier, the machinery supplier, the valve suppliers, and so on and so forth. And of course, nowadays, that's a huge issue. But that feed study is done. That may cost another $100,000. And then we get to the final stage gate, which is the final investment decision. So the company now may have spent $500,000 developing this PSA product offering and deciding now, are we going to start building these plants? Hopefully, if the decision is yes, they initiate that and the company swings into action, initiates all the EPC work that's needed, the factory testing, the field assembly, the adsorbent loading. If at that stage we say, no, we're not going to go through FID, we don't want to lose that information, again, we package that up and we keep that in the event that circumstances change and we may decide to go down that path. Once you've initiated your EPC work, you've built the plant, you've loaded the adsorbent in there, you go out to the field and you do the commission and performance testing and the operation and maintenance. There's always trouble at any PSA plant. There's always situations where it's not operating as it should. So there's always troubleshooting, there's always diagnostics, there's always analysis. A lot of this is automated nowadays, but that component is always there. And then finally, when the plant is operated to the end of its life, there's the decommissioning part. So that's the whole PSA workflow, all the way from an idea, all the way through to operation and maintenance of the plant. And you can see we had those 4 stage gates along that process that we had to satisfy in order for the adsorbent to actually see a useful outcome. And so it should be no surprise to you that 99.99% of adsorbents will never see operation in the field, because there's so many factors in this PSA workflow that have to be considered, and the adsorbent has to pass in order for that to work. So what I'd like to do in the remaining of the tutorial is to look at some of those steps that I highlighted earlier, and just give you some of my insights and experience over the years where I've worked in many of these different PSA systems. And I hope that I can give you some interesting things for consideration. And these are things that you can keep in mind when you think about yourself, if you're working in a laboratory making new adsorbents, or if you're working in a company and you're working on a process development unit in the pilot plant in the lab, whatever it might be. These are some of the factors, hopefully, that will help you decide. So if you're perhaps more of a chemistry adsorbent synthesis kind of person, and you've measured some nice material and you've measured CO2 capacity, let's say, and you've measured nitrogen capacity, you've got a nice separation, and you want to know, well, okay, can I run PSA? There's two questions you have to first ask yourself. What is the product? I'm trying to separate A and B. Let's say A is a molecule that's strongly adsorbing, and B is a molecule that's weakly adsorbing. It might be nitrogen oxygen from air. It might be CO2 nitrogen from a flue gas. It could be methane hydrogen from a hydrogen PSA stream from a steam methane reformer. So what's my product? Usually it works well if one of them is weakly adsorbed and the other is strongly adsorbed. What are the concentrations of those two molecules in the feed stream? And that's really important as well. Is one available in trace? Is one available in concentrated form? So if I've got a material that's available in trace form and it's strongly adsorbing, it's going to be very difficult for me to recover that material. Okay. So those two questions will provide a guide for the type of cycle that we use. And generally in pressure swing adsorption, I'm not going to talk about temperature today, but pressure swing adsorption, we generally separate cycles into two major categories. One is a category of cycle we call stripping cycles, where what we're trying to do is we're trying to remove the weakly adsorbed material as a product. And you can see in the cycle here, I'm feeding in A and B, and I'll see if I can turn my laser pointer on. I'm feeding in A and B. A is strongly adsorbed, B is weakly adsorbed. So A is absorbed at a high pressure, and B is produced as a pure product. And I collect that product, and that's my product that I send to the customer. I continue to feed. I divert some of that product as a purge that I'm going to use later on. And then I blow down this bed from a high pressure to a low pressure, and I recover all of the adsorbed molecules A, which I didn't want. I blow them down. They're not pure A because they still have a lot of B mixed in them. But then to really get the bed to be nice and clean before I start again, I flush out all of those A impurities with some of the pure B. Hopefully I don't lose too much of that pure B out the bottom. And then I go back and I repressurize the bed back up to the feed pressure. And I can add additional steps to that. That's very commonly done. But at its heart, this is the cycle called the Skarstrom cycle. And that's classically what I use to separate A and B, where B is weakly adsorbed and B is my product, and I want B as a high purity. So that's a very common cycle, and many people use that. The other classification of cycles on the other extreme is if I've got A and B in my feed stream, and A is strongly adsorbing again, but now A is my product. I want to recover A at high purity. I don't want B. B is a waste stream. So a typical example might be separating CO2 from flue gas using Zeolite X. Very strongly adsorbed CO2, and CO2 is my product. And I want to be able to collect that at high purity because either I want to sequester it or I want to convert it to something. And the waste stream is mostly nitrogen, and I'm going to let that go into the air. So you can see on the left-hand side, I'm going to feed A and B to my bed, produce pure B. Now, if I just went through the Skarstrom cycle, I would recover my A stream as in the previous slide, but it wouldn't be very pure. So to try and improve the purity of that, what I do is I try to readsorb, if you like, rectify or reflux some of that A back into the bed. So you can see in this step here, I've taken some of my A product, which was pure, and I fed it back into the bed. It's displaced some of the impure B material, which I take out the top. I've also reduced the pressure to an intermediate pressure, and then I blow down that stream, and now I get very pure A, and I can then take that pure A as my product, divert some of it back into the feed. So it's as though I've done a refluxing, and the names of this rectifying stripping comes from the distillation analogy, where the top part of the column is doing stripping, the bottom part's doing rectification. And it's almost like a reboil, the analogy with a distillation column. And then once I've completed my blowdown, I could do a purge if I wanted to, just to clean up that bed a bit more. And then I can do a repressurization all the way back up to the feed condition. So these cycles are called rectifying cycles, and they depart from the scarcum cycle because they have a recycle of the puree. And those ones give me very high purity of my strongly adsorbed component. So those are the two cycles that you can choose between, depending on which one is your product and which one's strongly or weakly adsorbing. And then the third type of cycle, which I'm not going to talk about, are dual reflux cycles. And those are more modern and more they're quite rare because they're difficult to get to work, and I'm not going to talk about them today. But they are cycles in which you produce both pure A and pure B. You have to do more work to do that separation. And so only in those instances where you need both of them in high purity would you consider such a cycle. But there may be instances where that's the case. Okay, so you now know what cycle you want to use, and you have an idea of what pressures you want to use. You'd like to determine what temperatures you should operate at and what specific pressures, particularly if you're going to use vacuum conditions. Many isotherms, adsorption isotherms, show most of their change in capacity below 1 atmosphere. And so it should be no surprise that vacuum sealing adsorption is very popular because that's where isotherms change a lot, is below 1 atmosphere. And so I've shown on the left here an adsorption isotherm. There's the loading, there's the partial pressure of A and B. The orange one is the adsorption of A. The green is the adsorption of B. And you can see these horizontal lines reflect the feed partial pressure of A and the vacuum partial pressure of A at those two levels. And you can see the amount of the change in adsorption from the isotherm and between those two levels corresponds to what I call the working capacity of A. And I do the same thing for B, that's the working capacity of B. So when I get asked to design a PSA for a particular adsorption isotherm, the first thing I do is I look at the isotherms, I look at these working capacities, I choose different high and low pressures where I can. You can't always choose different high and low pressures. Sometimes the high pressure is fixed by the system, and sometimes the low pressure is fixed by the system, but you do what you can, and you calculate these working capacities, and you divide them, and that gives you what I call the working selectivity. Now, a couple of comments about that. Many people will use the capacity of A divided by the mole fraction in the feed, divided by the capacity of B divided by its mole fraction in the feed, and say, that's my selectivity. I found that selectivity calculation to be very unreliable and frankly incorrect. We're not operating a distillation column, we're operating a PSA, and the conditions at the end of desorption are as important, if not more, than the conditions at the end of the adsorption step. So both need to be considered in the calculation of selectivity. And this measure I have found through the years to be not perfect, but reasonably good indication of how my system is going to perform. There's a couple of points I've indicated down here for people to be aware of. PSA is pressure swing adsorption. And even though it doesn't say anything about temperature, it shouldn't surprise you that there is a large temperature change when we do PSA. Adsorption is exothermic, desorption is endothermic, and because of that, and because of the very low heat transfer out of a bed, you tend to get very large temperature changes. And so you may need to account for those temperature changes when you do this working capacity calculation, and I'll show you how to do that. So I do this calculation, I change the feed and vacuum conditions or the feed and blowdown conditions, and I calculate working capacities and I plot them up, and I have a look and see where these capacities are making sense. I have to do this with isotherms. I can't use linear isotherms because they don't change in their capacities as you go up and down in pressure. So how do I account for the effect of temperature? So this is a very simple procedure to do that. If you've measured the isotherm of your material and you've measured them at sufficiently high number of temperatures, maybe you've measured them at 3 temperatures, that's enough. You've done a full isotherm fit, you've got the heat of adsorption, you've got the effect of temperature, then it's relatively easy to do this calculation here. So if you have N as a function of YP, which is partial pressure, and a function of T, which is temperature, you can calculate all these terms on the right-hand side. This is the change in loading with change in mole fraction. And then you can calculate the change in temperature with change in mole fraction and partial pressure. And so you can essentially do the calculation for an amount of material which starts at 300 Kelvin. Let's say I start dosing it with CO2. I increase the partial pressure. As I do so, the temperature increases. And as the temperature increases, the isotherm changes. And as the isotherm changes, the amount of loading changes. And as the loading changes, the temperature changes. So you can see this integration solved by these two equations here. And so I go from an isotherm, which is that solid line, to what I call an adiabat, which is that pink line. And that's the line I should use to do my calculation of working capacities. You can see it's much smaller than the isotherm. And doing what I call adiabatic working capacities and adiabatic working selectivities, that gives me a much more accurate measure of where I should be operating. And I repeat this analysis, and this is all done off isotherms. I haven't done any PSA simulations. If I repeat this at different temperatures, you can see I can generate a nice plot. This is a working capacity and working selectivity for carbon dioxide, nitrogen on 13x. And I've started at different temperatures, and I've plotted the adiabatic working selectivity. And you can see for 13x, contrary to what you would think, just looking at isotherms, if you looked at isotherms, you'd say it works better at lower temperatures. It doesn't. It works better from a working capacity and working selectivity as the temperature goes up. And it reaches a maximum around between 60 and 80 degrees C. And at those conditions, the working capacity is maximized and the working selectivity is maximized. So that's a way that I can then say, well, if I were to really build a system, if I'm able to operate it at 60, that's probably where I want to design the system. Now, I may not be able to operate it at 60 because that means I may need to heat the gas. I don't want to heat the gas necessarily. I may decide that the cost of the heat exchange outweighs the benefits I can get from the VSA. So I'm going to put that aside, and I'm not going to do that. But at least these kind of very simple calculations give me a starting point for my analysis. So that's the early stage analysis that I do. I mentioned earlier about impurities, and I think it's important for PSA engineers to think about this very early in the piece, because it will affect not only the design of your later work, but it may even affect your decision to continue or not in your program. Because as I've said before, I've been involved in too many PSA systems where the impurities kill the entire project. There will always be impurities in a stream. There may not be tough impurities, but there may be tough impurities. And I'll give you an example. This is a system we've looked at very recently that we've published on, which is a situation where hydrogen is introduced into the natural gas pipeline, and then we're trying to extract that hydrogen. Now, natural gas is not CH4. Natural gas is everything. It's got CH4 in it. It's got C2, C3, C4, C5, C6, and on it goes. It's got nitrogen in it. It's got small amounts of CO2 in it. And for good measure, for OHS reasons and as an odorant, mercaptans are added to it so that if there's a gas leak, you can smell it. All of those things present themselves to the PSA. And so you have to try and work out how you're going to separate that. And a lot of those molecules are very, very difficult to separate on conventional adsorbents. And so you may need to find very specific adsorbents, which you can do. And you can see in our configuration here, we've got a multi-layer bed. We've got a pre-layer of a special material to remove some of these contaminants indicated here. We've got a main layer to move CH4 or methane. And then the nitrogen, which doesn't absorb strongly on the methane, will slip through, but we don't want that to go into our hydrogen stream. So we've got a top layer of lithium LSX to remove the nitrogen in the top layer. So you can see it is possible to do a separation on a material, even if that material is not tolerant to impurities, by using multi-layer beds. So if you're working on an exotic metal organic framework which provides a very nice separation, don't be discouraged if it's contaminated by water and collapses. It might be possible to protect it so that it never sees water in its life. But it might also be that those impurities are so tenacious, you can't get them off under PSA conditions, and they will propagate through the bed and destroy the system. So it is important to look at the impurities early on. Once you've done that early stage, I now want to talk about the more detailed work. So this is the detailed simulation work that you do before you get to your experimental stage. So you've gone through the process, you've done the simple work, you've come up with the rough temperatures and pressures you should operate at, you're now going to go to your PSA simulator. And to do that, you need reliable adsorption isotherm data. In my experience, the leading cause of mismatch between models and experiment is inadequate isotherm data. There could be other reasons, but this is the leading reason. It's always the first thing I look at is my isotherm data good? Is it both, not just the data, is the representation good? And if I've got a lot of components and I'm seeing all those components at the same time on my adsorbent, it's very difficult to measure multi-component data for 3, 4, 5, 6, 7 components in a system. It could take months of experimental work to do that and very expensive. So in your workflow, you don't want to do that. You may have to take some approximations at that stage, but that's going to be a major input into your PSA. Kinetic data are reasonably important at this stage. If you believe your separation is mostly equilibrium, then you can just take a more approximate handle of the kinetics. But if your system that if you know is going to be dominated from kinetics, either from discussions with the people who made the adsorbent or from the data that you have, then you really do need decent kinetic data. And I suggest there's 2 systems there. One is direct air capture, which is strongly dominated by kinetics. One is nitrogen PSA, which in fact relies on kinetics. So those are systems where you will need good kinetic data, otherwise you won't have a separation. And again, you may have to get that. At this stage, it's too early to go through breakthrough or TGA. And then the final thing is your approach to cyclic steady state. Make sure you run your simulations enough in order to get there. And just because I needed to put some maths in, I'm going to put some equations in. For those of you that have done PSA simulations, this is all bread and butter stuff. For those of you that haven't, these are not very intimidating. One is a mass balance equation for a particular species. And nowadays we have commercial codes that grind through this in no time at all. We have an energy balance that keeps track of the energy flows up and down the bed. We try to account for the pressure drop in the bed. This is really important. May not be important in a lab, but it's very important in a process to understand what that is. And then our representation of the kinetics and the equilibrium are all equally important. And this set of equations is what we call the PSA simulation, together with all the boundary conditions for all the steps. And if you're operating as a chemist and all you're looking to do is really assess this through PSA simulations, it's not something you do in a couple of days. You may be able to access simulation programs such as Aspen Tech that make Aspen Adsorption, PSC, make GPROMs. You may even have custom models yet you can run, but there's a lot of experience and understanding in setting up and running these models. And so that will take you a little while to learn how to do that. So now that you've got your PSA simulations, bed pressure drop, as I mentioned before, if you expect it to play a role, you need to include it. You need to have enough resolution in your simulation, and you need to understand that your bed has to be scheduled with many other beds. You're not only going to run one bed in a real process, you're going to run multiple beds, and so there's a scheduling that you need to understand. One of the things that I discovered early in my career is, even though PSA looks on the face of it to be fairly straightforward, and the thermal effects appear to be fairly small on the face of it, they can accumulate and propagate and become very important. And one of the factors that I've seen in oxygen VSA systems, and we published this looking at the date now, that's 20 years ago, but very small thermal effects can accumulate over long times and cause large effects on the overall system performance. And you can see here an example of a temperature profile. And in a bed, the bed is 1.5 meters long, or a little bit more, maybe 2 meters. This bed has got a pre-layer in it to remove moisture. And you can see what's happened is it's caused a temperature depression. And we've published and analyzed this extensively. It's due to a regenerative heat exchanger effect. And that's caused minus 15 degrees C to occur. And then in the field, this might be minus 30, minus 40, minus 50. A very large thermal effect, which was not seen in the lab. And why wasn't it seen in the lab? It's a very tiny thermal effect. And the heat transfer in a lab unit completely masks and removes that effect, so you don't see any of that. And so you need to be really careful about that. You will see it in numerical simulations if you're careful enough. So these are things to be aware of in a PSA simulation. Initially, how do I choose bed sizes? I look at bed diameters, I look at bed heights, I look at gas flows. The way I do it is I look at gas velocities and I calculate pressure drops. If the pressure drop's too low, I'm going to get channeling. If it's too high, I'm going to get crushing. Choose a reasonable number. And that gives me a bed diameter, because your PSA simulation needs a bed diameter. So your early simulations you can do with fixed volumetric flow rates. Later on, you need to use machine curves. And then based on that, I can do a simple calculation of productivity, purity, bed size factor, sensitivity analysis, and I can then come through and calculate a cost. And this is my early stage PSA simulations that I go to my boss with, and I say, based on what I have and what I know, this looks like a prospective case. So now I want to turn a little bit to discuss the experimental work. This is the fun part as far as I'm concerned. Your boss has given you the go-ahead to go and actually say, well, okay, you think this will work? Go and build a PSA in the lab for me, and show me that it works with this adsorbent material that you've got. And so I want to just, rather than go through the procedure, I want to just give you some tips about what I think is important if you're designing and building a lab scale PSA system. So this is Paul Webley's tips on PSA 101 if you had to go into the lab and build one. The first thing that you always have to think about is, how big should I build it? Should I build a tiny one that sits on a bench top, or shall I build a large one? And obviously the answer is, well, what do you want to find out? The bigger you build it, the better it will translate to a large scale process, but the more costly it will be. And the costs are not just the capital cost of building a bigger PSA. Remember, you're using gas here to separate. And if it's air, well, that's relatively cheap. But if it's not air, if it's separating a synthetic mixture of CO2 and nitrogen, or a mixture of biogas that's synthetic, or an ethylene hydrogen separation, or a hydrogen stream from an SMR, whatever it might be, and you're going to run this off cylinders, that is a very expensive operation. And you want to limit the size of the vessels to limit the use of gas. Secondly, if you're going to use an exotic material that your whole process is predicated on, can you get kilogram or at least hundreds of gram availability of this material? And can you get it on the time frame that you want? And so the smaller the system, the cheaper to operate and to build, but the more unreliable the data. And so that's a qualitative decision, a call that you have to make that locks you into a system size. And so once you've basically decided, okay, this is how much gas I want to process, this is how much adsorbent I can afford to use in my experimental work, what about the L over D ratio? What should I do? And because later on when we scale this up, we're going to basically make the bed bigger diameter and keep the height the same. Try to make the bed height the same as what you're planning to use ultimately. So if you're going to plan to use a bed that has a height of 2 meters, build your lab unit to be 2 meters high. If you're only going to use a 1 meter bed height, then build a 1 meter bed. Now you may say, well, my roof space isn't high enough to build a 2 meter bed. Okay, build a shorter bed, but make sure that your system has at least 5 mass transfer zones in it. So you don't want to build such a short little bed that by the time the fluid has been admitted and the feed step has started, it's already bled out through the top. You need to have, in order to approach what you believe to be realistic data for your real plant, you need to eliminate these end effects, these startup, these non-constant pattern effects. So you need to try and get at least several mass transfer zones in your bed. So try to get the height the same as you can. And your diameter will then follow based on the velocity of the gas, the throughput, how much gas you can afford, and how much adsorbent you can afford. I would always encourage you to build multi-bed systems. Don't build a 1-bed system and hope to try and extrapolate that to a 4-bed system. Almost all of your PSAs will have bed-to-bed connections, and so you're going to have to need to actually measure those bed-to-bed connections and see their effect. Many of you will have done breakthrough runs using mass flow controllers. Don't use them for PSAs. Real PSAs don't have mass flow controllers. They have tanks, blowers, vessels, valves. Everything is pressure-driven flow. So you have a high pressure upstream, you have a low pressure downstream, you have a valve. And so the more you can mimic that in your lab unit, the more accurate your data will be. A poor mass flow controller in any step in a PSA will have its work cut out trying to keep track of flows that are changing from a factor of, with a factor of 1,000 in flow rates during a step. So I would caution against using mass flow controllers on a PSA rig. On a breakthrough rig, that's fine, but not on a PSA rig. One of the things you want to do in your lab PSA is you want to mimic the effect of bigger and smaller machinery. So for example, you may want to have a smaller vacuum pump. You want to run along a longer cycle time because you believe your kinetics are slow. So you want to have a smaller vacuum pump. Or you might want to run a very early fast cycle. Maybe it's a medical oxygen PSA and you want to blow down very quickly. So you want maybe a vacuum pump that's very large. You don't want to have to buy 10 vacuum pumps for your lab. You only want to buy one. So the way you mimic different sizes is you have the vacuum pump and you have a valve in line and you throttle the valve. In a real plant, you're not going to do that. You're going to match the vacuum pump with the process and you only have one pump. So your flows are restricted. One of the things that's bitten me more than once is correct sizing of the feed and blow down lines. When you blow down a bed from a high pressure to a low pressure, that's a lot of gas that has to leave the system in a small amount of time. The line size has to be big enough. And if it's not big enough, there's nothing worse than waiting for a system to blow down when the adsorbent is very fast adsorbent and you just have to sit and wait for gas to blow through a small pipe. So make sure that you've got that sorted out. Flow meters are very, very problematic for PSA systems. Almost all of the commercial ones have an issue. Why? Because they have to go from zero flow at the start of a step. You can imagine a blowdown step. I have a bed that's at 10 bar. I have atmosphere at 1 bar. I open a valve. I have a very high flow rate initially. And then at the end of the step, I have no flow rate. So I have an infinite turn down. And there's almost no flow meter that will give you infinite turn down. There are some flow meters that I've discovered, such as Anubar, which uses the orifice principle, that have very rapid response. And so I've had some good luck with those using that. My own DP cells, very rapid DP cells, and using my own routines to calculate flow rates. I've had limited success. You can use multiple flow meters with different ranges to try and capture everything. But this is not a trivial thing to do. And you may want to invest quite a bit of time and money on making sure you can get the flow meters right. Why? Because you want to be able to integrate the data and get a mass balance closure. If you don't have mass balance closure on the PSA, you don't have confidence that you've reached cyclic steady state, and you don't have confidence in your data. The other option for flow meters is not to use a flow meter, but to put what I call a dry test meter or an integrator on the end of the processes and just accumulate the amount of gas. Those can be very accurate. You'll see them on your house and measure how much natural gas you've used. Those are very accurate because people charge you money based on how much gas you use, so they make sure it's accurate. And so those can be, in some limited circumstances, can be used. And try where you can, as the last of my tips, to use an adiabatic operation. This is not easy in a lab column. Even if you have a heavily insulated column, you have a thick wall, and the thick wall acts as a heat sink. And so it's not easy to keep your system adiabatic. But there are ways that you can get around that. And this just gives you an illustration of a system we built many years ago. I've built many since then. Typical 2-bed system. I've instrumented it with thermocouples up and down the bed. Very, very important for diagnostics. I've got some pressure transmitters. I've got a pre-dryer to remove moisture in this system. I've got a feed tank. And you can see I've got a position valve here. I've got a control valve, and I've got solenoid valves. And so my feed step will simply consist of opening a solenoid valve and having pressure here and pressure there and pressure-driven flow. And then from pressure in this bed to pressure in the product tank, I have another solenoid valve. And so everything is just pressure-driven flow and position valves. And that mimics the operation of the plant where I have the same sort of thing. In my vacuum pump, I've got a CV2, which is a position valve, which allows me to open and close that so that I can mimic a large or a small vacuum pump with a single vacuum pump. All right, so once you've built your system, how do you go about operating it? I always like to say start with some very exploratory runs. You don't really know where the system is. Start with your simulation conditions from your simulator. Identify your major variables which influence the operation. Usually high, low, feed, velocity, temperatures. There's a lot of variables in the system which are specific to your system and may not translate, such as step times. You'll have to adjust them to get the system to operate where you need it to operate to give you those high and low pressures and to give you the feed velocities. It's always possible to run a PSA badly by choosing the wrong step times. So you will have to muck about with step times a while for a long time. And then once you really understand where you're at, you then set up a grid and you start to generate your data systematically, statistically. You can analyze the data and you can create your Pareto plots of purity and recovery and productivity. And one of the things that you should really avail yourself of now, because they've become available, are all the tools of data mining and AI, which you can really use to reduce the operation space and the space that you have to explore. You can see that I've got, in this instance, 1, 2, 3, 4 variables. There may be temperatures, other temperatures, and purge flow rates and PE amounts and so on. There may be 6 or 7 variables, each one operating over 3 or 4 levels to vary. And if you really wanted to just use a full factorial design, you could be there for months and months and months running the system. So I would encourage you to look at some of the more recent opportunities to really expedite the experimental work. Make sure that when you make a change, that you do allow the system to reach a new cyclic steady state. This is a periodic system. When you create disturbances from the boundary, they propagate into the system and they take time. Some of them propagate quickly, some of them take a long time to propagate. In my experience in PSA, the very last thing that converges is the temperature. Everything else converges first. You get a perfect duplication of concentration profiles, pressure profiles. Your mass balance and your energy balance closures may even be good, but the temperatures are usually going to be the last ones to converge. And then one of the key things you want to do in PSA is you always want to run a PSA as fast as you can. Why? The more batches you get per day, the smaller the plant gets. And so, or alternatively, the other way around, if you run a particular cycle and you run it faster and faster and faster, you are able to get more and more throughput for the same size plant. So cycle time is one of the key variables in PSA. Keep an eye on impurities. Remember, you have to be able to purge them out if you're going to run the system successfully. So just to show you some examples of that, this is we looked at post-combustion CO2 capture from wet gas many years ago. In this instance here, we had a pre-layer where we trapped the water. And you can see here we have what we call the purge to feed volume ratio. If we run that ratio too low, this is the length of water loaded zone. You can see the water loaded zone is tracking its way through the pre-layer, and eventually it'll go into the main layer and start contaminating my main bed. And so it's very important to keep these variables at a key level to make sure you purge off the impurities. And I'll show you another example here of cycle time reduction. So cycle time is really interesting. Your PSA process makes a certain amount of product with a certain purity every cycle. And so that's what I would call the bed size factor, the amount of material you make per cycle. If you can run a lot of cycles per day, then on a day basis, you have more productivity. So try to run the cycle faster and faster. You can see in this graph, I've got a 4-step cycle here. I'm feeding, I'm making product, I'm depressurizing, and I'm purging. Just on a single bed, and I'm running that cycle faster and faster. And I start at 50 seconds and focus only on the stars. That's the experimental data. And so at 50 seconds, I'm producing 2 kilograms of oxygen per kilogram of adsorbent per day. And then I just decide to run that cycle faster, shorten all the steps, and I'm now suddenly at 3 kilograms of oxygen per kilogram per day. and I go faster and faster, and you'd expect a hyperbolic profile because the productivity goes as 1 over the cycle time. But at some point, in this case, when I got to 15 seconds, the very next point at 10 seconds didn't fall on my curve that I expected. It was around the same. And in fact, if I now start and go 5 seconds, I'll start going down. So what's happened here is some of those factors that affect the performance, the mass transfer and the pressure drop, have intruded, and I'm getting less per cycle. So even at 15 seconds, at 10 seconds, I'm getting many more cycles per day than I am at 15. I'm getting so much less per cycle that I haven't really helped my productivity. And so if I go any faster, I'll fall down. So that's a nice way of establishing where I should be operating my system. And this is another example of a 6-step VSA system, a 13x zeolite. You can see I've gone through, this is a new system we built recently, a very simple 6-step cycle. It's not a rectifying cycle, so I don't expect high purity. This is really just to show you the kind of data, how you should be reporting the data. Each of these curves was multiple adjustments of feed steps times and vacuum step times in order to keep the purity and recovery on track. And so these show the Pareto fronts that I can achieve at different vacuum levels and for different feed concentrations of CO2. So you can see there is a lot of experimental work. This will take you, if you're designing a system to be built, this might take you a year to do. Now, I'm also very conscious of validation of your model. So you've got your simulation model. You've got to be able to validate it against your lab data if you're going to use it for scale up. And a lot of people just take their model, they match it to the pressure profiles of the PSA, and they say, yep, fits well. It fit well with your recovery, it fit well with purity. I'm done. Everything's good. Well, maybe not. Look at this profile here. On the left-hand side is a pressure profile of a PSA. And you can see the dots represent the experimental data, reasonably good match of the data. On the right, you can see the match of the temperatures. So the dots are the temperatures, the high temperatures and the low temperatures in the bed. And you're seeing the high and the low temperatures on the simulation, and I'm off by a good 30 degrees C. So you really have to ask yourself, if you looked at the isotherm, how sensitive it would be over 30 degrees C. Although I match the pressure well, really, do I feel comfortable about using my simulation to scale up my data? So that was the experimental work. And I'd like to finish off today and talk a little bit about the feed, the scale up, and the operation. So I have a few more slides on that. So once you've got your extensive experimental work, you now need to go and scale up. And you need to work with your engineering company that's going to take your data and say, okay, if we're going to build a big PSA, what does it look like? One of the things with a small lab unit, and you don't even care about this in your simulations, is distribution of the gas. In a small 5-10 centimeter diameter column, you don't have to distribute the gas. You just bring in a tube in the top and the gas goes into the bed. On a large vessel, if it's a meter diameter, 2 meters, 3 meters, and you have gas barreling down the middle and hitting the surface of the bed, you can't have that. You need to distribute the gas. So this is something that you have to worry about. And to get the distribution right, you may need to add a lot of volume. And so you're adding a lot of volume to this bed that isn't doing any separation. But you have to do that. Otherwise, you're not using your adsorbent effectively. That's something to think about. When you go to actually calculate the size of the machine that you need for your bed, how are you going to do that? You didn't use a commercial machine for your lab unit, so how are you going to do this? So what you have to do is look at the intrinsic data from your bed, and the intrinsic data is every time you pulled a molecule out of your bed, the pressure changed. And so the moles removed versus the pressure is the intrinsic lab scale data that you're going to duplicate in the plant. And you're going to do that by matching that moles versus pressure to the machinery curve. And I'll show that in the next curve. So here is your moles removed versus vacuum pressure, or maybe it's just blow down pressure. And that's the curve you get experimentally. And what you're going to do is you're going to pick a vacuum blower or pick a machine. And in this case here, you can see I've got flow rate, deeper vacuum, and power. As I go deeper vacuum, I go up in power, and I go down in flow rate. And I have to integrate this curve against this curve. So what does that mean? I start at a particular pressure. I say, all right, I have to remove this many moles. and then my pressure will drop a little bit. At that many moles, at that pressure, this is an actual meters cubed. I start at a particular pressure, I drop down. What is my new volumetric flow rate going to be on this curve here? And so I'm continually integrating one against the other so that I can honestly say, if this bed is connected to this vacuum pump, will it pump down in that given time that I had in my lab? And so if it doesn't, if the time was too long, I've got to choose a bigger vacuum pump. If it was too short, I've got to choose a smaller vacuum pump. And that's how I go about choosing the machinery for my scale up. As I mentioned earlier, thermal effects, labs have got very high surface to volume ratios. Make sure to try and either mimic adiabatic operation or really be scrupulous about your simulations. Void volumes, if you're looking at very high purity materials, very high purity hydrogen for your hydrogen PSA, you will need to be very worried about void volumes, excess tubing, excess head volumes in a real plant. That will affect your results. And the other thing to remember is that a PSA doesn't just consist of beds and valves. There's things around it. There might be heat exchangers needed. If there's a compressor that was used to provide the feed gas, the gas will come out hot. You'll have to heat that. If there's a heat exchanger, you may have to do some cooling in that heat exchanger. There'll be pressure drop. You may have to do some compression of the product. All of these things will impact your process. You'll have to watch for fluidization in the system or gas maldistribution, as I've mentioned earlier. Finally, a little bit about operation and practical issues. Once you've designed, you've scaled up, you've built your system, and now operates. Now, one of the things that the system does is that you didn't do in your lab was you didn't run for 3 years, but the plant ran for 3 years, and gradually, for whatever reason, moisture has made its way into the system, or some contaminant, maybe H2S, has made its way in. You need to be mindful about that. You need to monitor that, and you need to understand that. There may be changes upstream and downstream which propagate into your system that you didn't mimic in your simulation or in your lab, and you have to understand what is the effect of that. Maintenance in the system is a lot around valves. They're the only moving parts in the system other than machinery. Startup and shutdown procedures are very different to the lab because your environment is not controlled. In the lab, we have a controlled environment with very exacting OHS standards, and so we understand startup and shutdown. In the field, shutting down the process is very different. Your process is connected to a customer. If you shut that down, the customer has to use a backup. How do you shut that down without disrupting the customer? How do you start it up without disrupting the customer? If you do bottle the system down and shut it down, how do you keep it idle? Remember, the adsorbent is a dynamic beast. It adsorbs when it gets cold and it desorbs when it gets hot, and the vessel is sitting in the sun. And so without you doing anything, its pressure is going up and down. And if it gets too cold and it starts to absorb a lot of its environment, is it going to start dropping in pressure and sucking in gas from the air? So these are the sort of things you have to think about in operation. OHS issues are always really important. They're not important at a small lab scale. You put a mask on, you have a beaker, you pour the adsorbent in, and you're done. On a very large scale, that's a very different story. Diagnostics, one of the things I found through practice in operating PSA systems, you can't access the profiles in the bed because you're not measuring them, and you're not measuring them because it's too costly to measure profiles in a bed while it's operating. But you can measure temperatures reasonably cheaply. You put some thermocouples in the bed, and so you can see where the temperature is changing, and you can measure differential pressures. So you can see where there is pressure changes and perhaps attrition of the adsorbent is causing more pressure. So that's a very useful diagnostic. And I'll just give you an example. Here's a system we've run with temperature profiles. We don't have any composition profiles, but using the mathematics of PSA simulation and understanding that the change in temperature at any point is due to adsorption and desorption, we can deconvolute this signal and produce a composition profile in the bed. And we published this many years ago, a very handy technique for effectively inferring what the system's profile looks like just from the temperature measurements. And that's very handy because I can do this computationally, I can do it in real time, and I can infer, am I feeding too much as part of my adsorbent diet? Is it no longer absorbing? These are the sort of factors I can determine. So in conclusion, we've come a long way from isotherms to a plant. There's a lot of information between finding a really nice isotherm or getting asked to do a separation and finding the isotherms and actually building a plant. But I'm very pleased to say, I think we have, as a community, as adsorption community, both engineering and academic, we have the tools, we have the knowledge. We've been working studiously on this for 50 years. We have the knowledge to minimize a lot of these oops moments that we have during our life, both with respect to experimentation, scale-up operation. And I'm particularly positive about the future for adsorption separations because there's so many new adsorbents that are being discovered, being synthesized, even a priori being synthesized. That's a very exciting development. But in parallel with this, we have such a powerful development in AI, which is helping us not just synthesize adsorbents quickly and more powerfully, but also reduce our development time and implementation time and reduce the discrepancy between the way we think the adsorbent was functioning at a small scale and the way it's functioning in a large plant. So I remain very positive about the future of adsorption. And there's a lot of good work for a lot of you who are starting in your journey through adsorption. And I thought I'd just show in my last slide some of the projects that I've had the privilege of working on. The top left-hand side is a few ton a day plant that separates carbon dioxide from a coal-fired power plant that has about 10-15% CO2 in the flue gas. You can see the 3 beds there. There's the vacuum blower. So this ran at the Hazelwood power plant about 3 hours drive from me for about a year. Gave us some really good data. This is a little lab unit that we built, a 4-bed PSA lab unit that's sitting in the lab at University of Melbourne. This rig over here on the right-hand side is a rig that separates CO2 and methane at very high pressures and is operating at the Otway Basin, which is about 3 hours drive from Melbourne in the other direction, and is used for testing some of the really interesting trapdoor zeolite materials. On the left hand here is a really interesting project I worked on with a colleague in India who, during the COVID scare, we were very concerned about lack of oxygen supply in India, and so I worked with him to build an oxygen VSA, and that project is now continuing and will continue as we roll out that product line. So that was a very interesting study. This little one here is a very niche, small PTSA, which separates CO2 from a syngas stream from a gasifier. Very challenging operation. There's H2S in that stream, so that was very difficult to get to work. This little plant here is a plant that we built to remove carbon dioxide from a bottling plant. So we have a lot of bottling plants that produce beverages, and they vent a gas that is about 60% CO2. And rather than vent that, we decided we were going to build a plant there on their site that takes that gas and enriches it back up to 99%, and potentially they can recirculate that and use it again. And on the right-hand side, you can see a 4-bed PVSA here. It's actually 2 systems, a PSA and a VSA, which takes tail gas from a hydrogen PSA and removes the CO2 and then enriches the PSA back up to the customer. So I've been very lucky to be involved in working at this interface between the universities and industry, and really seeing the application and the getting the experience of what matters and what doesn't in these scale-ups. And so with that, I'd like to conclude and thank you all very much for your attention, and I'm happy to take any questions.
Thank you, Paul. Very comprehensive tutorial. So we do have quite a few questions coming in. So I will start from the Zoom question. The first one is about the parameters for PSA simulation. The question is, how do we get LRC parameters for the PSA simulation? I'm assuming LRC is a loading ratio correlation.
Okay, so let me go back to the PSA simulations. This is the experimental work. So to get your initial simulations, I'm assuming what you mean by loading ratio correlations is the loading that you're getting at various operating pressures. And the way I do that is through these graphs here, through my working capacity graphs. And so you need to have your adsorption isotherms at a range of temperatures, and that gives me the high and the low pressures. That gives me the loadings that I need at those conditions. I'm not sure if that's what you mean by loading ratio correlations, but that's what I use for determining the initial set of pressures to operate the PSA at.
Yes, I think there is a follow-up question from the same person. So is that possible to share cycle and adsorption details for the CO2 separation process?
Is it possible to share isotherm details?
Yeah, for the CO2 separation process.
Well, okay, there's so many different details. It would depend very much on the specifics of the separation. So, for example, what's the concentration of CO2 and nitrogen? What's the adsorbent material that you're using? So there's many conditions, and many papers have been published on this. James, I think you've even published some papers yourself on this. So there's a lot of starting conditions. A lot of it depends on the pressure of the flue gas stream. So if it's a flue gas stream, right? If it's a flue gas stream, they're always at low pressures. And if they're at low pressures, you're always reluctant to have to pressurize them. So you're going to run VSA. Whereas if your stream is coming from, for example, a biogas process and has got a high pressure, you may be tempted to run a PSA. So I think I'm happy to share whatever information the person wants, but it's going to be very dependent on whatever the circumstances.
Okay, thank you, Paul. So yes, as I'm the moderator, I take the advantage. So I have a question. So in the first step or second step, you mentioned about the rough capex and approximate kinetics of the adsorbents. Okay. Sometimes it might be. Do you find it's hard to assess the capex, since usually you will involve compressors and vacuum pumps, and if you don't do detailed simulation, how do you size the compressors and vacuum pumps? And when you have the sizing information, how do you estimate the dollar cost?
Yeah, so I think so with a lot of PSAs, if you have, for example, a hydrogen PSA, then you don't need to worry about compressors and vacuum pumps and so on. But if you're running a system that does have compressors and does have vacuum pumps because you don't have any pressure, then that is something you need to worry about. So you can determine from these very simple calculations, working capacity calculations, you can determine roughly how much adsorbent you need, right? And you can determine if, for similar systems, for typical cycle times, and this is where you'd look in the literature and say, okay, everyone else seems to be running a cycle time of a minute or so. That gives me a certain throughput that I can expect. And from these working capacities and working selectivities, I can expect this recovery. And so that gives me a rough idea of the flow rate, moles per hour. And if I know an average or a low vacuum pressure that I'm expecting, that will give me a volumetric flow rate. And from that, I can go to the charts of vacuum pump versus size and choose a rough size vacuum pump. Even at the early stages, I can look at a chart of vacuum pumps and say, okay, I think for this application, so for this throughput, so you'll always have to know how much gas does your customer want, what's the throughput, and work your way back from recoveries and vacuum pressures, what the vacuum size has to be. And once you have the vacuum blower size, you're able to get a rough cost. Now, you can either do that by looking at literature data for vacuum blowers and costs. There's some books that, Aspen might give you sizes from the economics database of what that would cost. But there is a way of doing that, and you have to do that early, roughly. That's why I said plus or minus 50%. If you wait until the detailed PSA simulations, you may have put a lot of work in and wasted a lot of time. I found with a simple MATLAB model that I can get a rough idea of vessel sizes, adsorbent amount, and feed and vacuum blower sizes to within 40, 50% at the very early stage before I do PSA simulation.
Okay, thank you. So I think we have a follow-up question regarding to the vacuum pump. So this question is from YouTube. So it's about the vacuum pump selection. So if we don't consider the cost factor of a vacuum pump, is a larger vacuum pump always better than a smaller one?
I'm not sure how I would answer that question, because large is a relative term. So, when you get to, so firstly, the selection of the vacuum pump is going to be strongly dictated by the lowest vacuum level you want to get to. So if you want to go to, let's say you only want to go down to 30 or 40 kPa, I can use a single stage vacuum blower, relatively cheap, and achieve that. If I want to go down to between 5 and 15 kPa, maybe I need to use a liquid ring vacuum pump. Liquid ring vacuum pumps are available in a smaller scale. And then if I want to go much deeper than that, then I'm going to have to consider far more exotic materials. So if you go back to the vacuum vendors, you'll find that depending on the vacuum level you want to achieve, certain machines are appropriate for those vacuum levels. So that's the first thing to say. And then they would be available at different sizes. The more shallow the vacuum, so not going very deep vacuum, the bigger the vacuum blowers can be. And that's for logical reasons. So you may find that you may be forced into a small vacuum blower simply because you want to go down to a very deep value. But if you had a choice between big and small, it all comes down to your system design. So for example, if you want to pump your system down to 10 kPa, and we've done this with CO2 VSA, and we find we have to go down to quite a low vacuum in order to get a reasonable purity. If we want to go down to 10 kPa, you then have to ask yourself, okay, I've got a bed that's a meter in height. I've got 10 kPa at the suction and then at the vacuum pump. I better make sure that the pressure drop in the bed is no more than 1 kPa, because I don't want it to be 15 kPa at the top of the bed. I want it to only be maybe 10 or 11 kPa. So I need to design my bed in such a way that the pressure drop is not very high. Similarly, the pipe that connects the bed to the vacuum pump, how big do I need to make that pipe so that I don't have a large pressure drop in that pipe? Because every kPa, 1 kPa out of 10 is 10%, and has a dramatic effect on the adsorption isotherm and consequently the purity. So these are all the factors that you have to consider. You may find that you don't really have the luxury of big or small. Where you can, run the cycle as fast as you can. Obviously, that means that you have, if you want to try and get more and more throughput, you need a bigger and bigger vacuum pump. But I don't think you always have that luxury of making a choice between big and small.
Okay, thank you. And on the pressure drop, do you find it's normal case that the simulation can always capture the pressure drop in reality?
I found we published a paper on this many years ago, exploring whether the pressure drop calculations of the Ergen equation were reliable for adsorption systems. And our conclusion was, yes, it was reliable. So you can capture the pressure drop accurately in a packed bed. Where you may not capture the pressure changes accurately is if you have very rapid pressure changes, where you have momentum transfer, which is not typically captured in a PSA model. So PSA models don't solve the momentum balance. You'll notice my equations didn't have the momentum balance. We've basically said that momentum conservation is dominated by pressure drop in the bed, so we're just going to solve pressure drop. But there are instances that I've seen in the field where you open a bed very rapidly and you get very quick changes in the pressure of that system, and it's all around momentum transfer of that gas, and that's not in the Ergen equation. And so those pressure changes, not pressure drop, are not accounted for. But if you wanted to, you could potentially include those equations in the simulation. But all other things being equal, I found the Ergun equation is a pretty reliable measure for the pressure drop in PSA systems.
Thank you, Paul. I think this we have several more, but I think this one is more related to the practical operation of PSA. So this question is, in a two-bed VPSA system with pressure equalization step, there will be discontinuity in feed as well as tail gas flow, product gas flow. So in such cases, how do we run the vacuum pump? Should we consider additional tank? And another question, I think, similar in this same perspective.
That's a very That's a very good question.
I allow you to answer this first.
So when you have a cycle schedule in a PSA system which doesn't match the desires of your machinery, then you have to decide what you want to do. If you've got a vacuum pumps don't want to be turned on and off; they want to run all the time. And if the vacuum pump isn't connected to something, what are you going to do with it? And you're just wasting energy just running it. So the logical solution is, don't build a 2-bed PSA, build a 3-bed PSA, and change your cycle so that you always have a bed on vacuum. So that's the first opportunity. Second opportunity or possibility is during your PE step. Do the PE, let's suppose your PE step is 10 seconds. For the first 5 seconds, do PE, and for the last 5 seconds, open the vacuum valve, and during the PE step, what I would call dual end PE, and start the vacuum pump early, and see if you can operate like that. The third way is to accept that I don't want to build a third bed. I'm going to have to run the vacuum pump. So you have to put a recycle loop around the vacuum pump with a valve, and that recycle valve opens. And so while the system is idling and then you're doing a PE step, the vacuum pump is running on complete idle. It won't get too hot because you're only doing it for a few seconds. So those are, I guess, 3 possibilities that you could consider to do with your machinery. You can't turn your machinery off; it has to run, and you don't want to deadhead it. So those are some of the options for you.
Thank you. I think another practical question from the same person: how important is the floating mesh screens between different adsorbent layers in an adsorber?
So they are important when the materials that you're trying to separate have got different densities and different particle sizes. So I've had circumstances where we've had a floating mesh screen between 2 layers. The screen is, for whatever reason, broken or come away or torn, and the one material has made its way into the other material. And over time, we've all had breakfast cereal where, you shake it and the big pieces go to the top and the little pieces go to the bottom. And that's what's happening in a PSA. It's a bed that's being vibrated all the time. And if given a chance, the big particles will go to the top and the little ones will go to the bottom. So it is important to have a floating bed screen between layers, and hopefully you have a way of anchoring that screen so that it doesn't get destroyed, and it must be allowed to move as the beds settle.
Thank you. I think before time we have so many questions, so I will just pick another 2 and then we wrap up the session.
I'm more than happy to, if the questions are somewhere available typed in, I'm more than happy to, over the next few days, just answer them just by typing an answer if that facility is available somewhere.
It's some questions are on the Zoom Q&A session, but I will ask the 2 questions from YouTube. The first one is that in your working capacity estimation or initial calculation before simulation, how do you estimate the bed conditions before and after A and B recovery? Just a pressure?
I don't understand the question, James.
So the person asked, in the working capacity calculation.
So the graph that I have now.
Yeah, exactly here. So before simulation, so that's before simulation, How do you estimate the best condition before and after? Is it before or after?
I see what you mean. Okay.
Yeah.
So basically they're saying, how do I pick those points?
That's right.
So that's actually a very perceptive and very good question. So before you start recovering your molecules, let's say it's a feed step, right? So we know the feed temperatures and pressures and mole fractions, so we can choose that number. The difficulty is when we're after we've removed the gas and we're at the end of, let's say, end of vacuum, we know the pressure, we can calculate potentially the temperature, but we don't really know the mole fraction of the gas, because you kind of have to do a more sophisticated calculation to calculate that mole fraction of the gas. So there's a couple of ways around that. A, you can do that more analytic calculation. It's a little more numerical. Perhaps you can even do it in Excel. But B, choose a relatively high value for your concentration. So for example, let me be specific. Calculating the working capacity of carbon dioxide from a PVSA bed when I'm pumping it down. So I start off and I say, all right, before I recover the CO2, my bed is filled up with a gas that is 15% CO2 at feed conditions of 1 atmosphere, and it's on an average temperature of 30 degrees C. So I look on my isotherm, I can identify that point. And then I say at the end of vacuum, I'm going to use an adiabat. So at the end of vacuum, I'm going to pump down to 10 kPa. I'm going to be going down to, and I calculate the temperature and I drop by 20 degrees C. So I'm now down at 5 degrees C and I'm at 10 kPa. And I'm going to say, I don't know what the purity really is. I'm going to use a value of y CO2 equal to 1. I'm going to assume it's pure CO2. Okay. I know it isn't really pure, but that's going to give me my starting condition. And then eventually when I start, that'll be good enough to get my PSA simulations going. And then I'll be able to see from the PSA simulations that I actually only got to 80% purity. And so that's my concentration should be 80%. So it's a little bit of guesswork, conditions before and after. It's important you don't just use conditions at the end of feed, because when you pump down the bed, you didn't start at the end of feed, you actually started at the end of an equalization step. So you need to try and estimate the best you can the conditions at the start of recovery, before you recovered your molecules, and the conditions after recovering molecules. So there is an element of guesswork in there.
Thank you, Paul. The last one is a high-level one. Do you think adsorption will stand out against other competing technologies for commercial carbon capture? Will that be VSA or TSA or hybrid?
I think that's a good question. I think the CO2 by adsorption capture will have a role to play in direct air capture. It already has. We all know that. I think it will have a role to play in capturing CO2, for example, from tail gas of hydrogen PSA. It's already being used for that. There'll be applications, we were looking at capture from a cement plant where the scale, the throughput is consistent with the size of vessels and blowers that we can buy. I do not think we will be using adsorption to capture CO2 from the flue gas of a coal-fired power plant. But then personally, I don't think we'll be using anything to capture CO2 from a coal-fired power plant. I think we'll be changing from coal to something else. But I think there will be a role for adsorption, always be a role for it in CO2 capture in the smaller scale of things. And as personally, I'm starting to work in CO2 utilization, there's a lot of applications where there's a CO2 stream at a relatively small scale that we want to remove that CO2 and then we want to process it with biological means or some other means. And we don't want to introduce chemicals like amines in there. And so for that scale and for that environmental reason, adsorption is very well suited. So I think my answer would be a resounding yes, and growing in the space where CO2 utilization is important.
Thank you, Paul. I think that wrap up the Q&A session. Now I'm going to hand over to Dr. Jun.
Thank you, James. Wait a moment. I share my screen. Thank you for your informative presentation, design, operation, and analysis of pressure swing adsorption processes. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Webley with an announcement of the IAS Twitter feed. The hope is that the work discussed today will be a useful resource for the Adsorption Science Committee in the future. We don't have the webinar in December. The next webinar is now in the planning, but as I mentioned at the beginning, the third IAS Twitter Poster Conference will be held next week. Please consider joining us if you're interested. Announcement regarding the next webinar and the IAS online event will be posted on our Twitter feed and through the IAS mailing list. With that, we thank you for joining us. We hope that you will join us again soon. Thank you.